Zainab, how are you? I'm audible?
Yes, sir.
You were absent in the previous class. Why? Why didn't you take the previous class? Are you busy?
Sorry, sir.
Why didn't you take the previous class? I'm audible
Sir,
to
you're
you?
not audible, sir.
Hmm?
Sir,
You were
you are
having.
not audible.
I'm not audible. Wait a minute.
Yes, sir. Now you're audible.
Okay.
Sir, we were doing the occurrence of metal, the sulfide ore and carbonate ores.
Carbonates ores. Okay. Have you done your examination? Chemistry exams has been done. Science.
No, sir, it's next Thursday.
It's on next
Thursday.
Thursday. So, is there any specific topic that you want to study because you are on one-on-one?
Sir, occurrence of metals is also there and half of carbon chapter, sir.
Half of carbon. So, should I complete this metallurgy portion because this is very important? Okay.
Yes, sir.
So, up to where we have studied calcination roasting done. Let me check where up to where we have studied for.
Sir, till advantage of roasting.
Advantage of roasting calcination cell. Metallurgy. Carbon is compounded. Okay, we studied metallurgy. Up to advantage of roasting and
Metallurgy, sir. Sir, advantage of roasting and calcination.
okay. So you have noted this one. Okay. Now moving to the next part. Have you noted this one? Have you done this one, or we should try it from here?
Yes, sir, we finished this one.
We finished this one. Okay.
Yes.
So now moving to the next part is that roasting, and we can why we are doing calcination roasting. First of all, let me explain you again that actually we have four types of ores: sulfide ore, sulfide ore, carbonate ore, then oxide ore, and then halide ore. Halide ore. This is very reactive, so we are not going to touch this one. Okay, this is oxide form, already in oxide, already in oxide form, and these two are, this is sulfide ore and carbonate ore. This we convert it into oxide form by roasting. By roasting, we convert it into oxide form, and by carbonate is also converted into oxide form by calcination. Calcination. It is also converted into oxide form. So why we are doing this one? Why we are doing like this? Because it is easier to extract out metal from
Oxide form, sir.
oxide form than their carbonate or sulfide forms. Okay, you understood? Now
Yes,
moving
sir.
to the next part here is that we are having different types of ores. Like first of all, let me take metals. Like we are having sodium, then potassium, sodium, calcium, magnesium, aluminium, then manganese and chromium, then carbon. Then we are having zinc, iron, tin, lead. Then we are having hydrogen here, then copper, then silver, then gold, copper, mercury, silver, gold, platinum. As you know that these exist in their native state. These elements exist in their native state, and these elements Hg, I have written Au, Hg, Ag. These elements from their ores, like if it's Cu, then it occur in the Cu2s form. This is Hg, it occurs in the form of HgS. And this is Ag, it occurs in the form of AgS. Okay. So
Yes, sir.
if they are existing in their oxide form, sulfide form, then they can be extracted by simple roasting. Simple roasting is just to heat it and you will get the metal. For example, if you have Cu2s, okay, if you have if you have Ag2s, Then you heat it in the presence of oxygen. Roasting, it is heating. And heating in the presence of oxygen is called roasting. It will be converted to Ag2 and then SO2. And then further this Ag2O, when you keep it on heating, it will gives you Ag plus O2. Okay. Similarly, HG S plus oxygen will gives you Hg plus SO2. But when this HGO further heated without any reducing agent, then we have Hg plus O2. Since these Hg and Ag are below copper in the reactivity series, as we move upward in the reactivity series like copper, mercury, silver, Ag. This is mercury, and this is silver. So these are below copper. As we move upward, we need a reducing agent for removing the for reduction. Okay, for removing the oxygen. So if we are having Cu2S and we heat it in the presence of oxygen, it will gives you Cu2O plus SO2. Now alone, if you heat it Cu2O, then it will not give you Cu plus SO2. Here we need a reducing agent. Here we need a reducing
Agent.
agent. As in the previous one, we were just heating only AgO and HgO. Here you can see. In the second step, we are just heating HgO, A2GO, A2O. Okay, but here, what we are going to do here is, we need a reducing agent because this is reactive. Copper is reactive in silver. So this bond cannot be broken. So we can done it by carbon also. If it is, we are having only this one. But actually, here we use crushed ore. Crushed ore itself behave as a reducing agent. Cu2S, when you heat it, it behave as a reducing agent. It will give you Cu plus SO2. So here we can say that crushed ore itself behave as reducing agent. You understood? Crushed ore itself behave as reducing agent. You understood?
Yes, sir.
Okay. So where we are not going to have another element that we are using here to remove the oxygen. The reducing no external reducing agent is being used here. We just use simple the crushed ore. Okay, the crushed ore itself. For example, some of the particle has been converted into this one, and this will start reacting with the particle of Cu2S, which is not being converted till yet. Okay, so crushed ore itself behave in the reducing agent, but in above three, we are not using any external reducing agent. Okay, so all the three can be, we can say that all the three can be obtained like Hg, HgS from, we can say Hg from HgS and Au from Au2S and Ag2S and these copper from this. These all three can be obtained by simple roasting. No external reducing agent is being required. Okay. So have you check in your copy? Have you noted this one?
No, sir.
Not noted, now. Okay, so noted down that here a crushed ore itself behave as a reducing agent. Okay, after this one. So by simple roasting, you can extract this one. Note it down. Note this one. Note all these three equations. And note for this one that crushed ore itself behave. Note here crushed ore itself behave as a reducing agent.
Sir, only for Cu2S I have to write?
If you have noted this one, then no need to write it. But if you have noted this, not noted this one, then you have to note all these.
Okay,
Six.
sir.
Done?
Yes, sir.
Okay. Now moving to the next part, here we have now another one. If we are talking about this one, now if we move further, as we move further, we will find that there is a difficulty in removing the oxygen, because we have just converted all the sulfide and carbonate ores into their oxide form. Okay, now if we were having zinc in the form of ZnS, now we have ZnO. If we are having lead as PbS, now we have converted into PbO. Okay, and Fe2O3 is already in FeS form, and if we have iron in Fe2S form, then it is, sorry, or FeS form or Fe2S form, then it is still get converted into FeO form. Okay, so we have converted all the major sulfide and oxide ores into their, sorry, carbonate ores into their oxide and oxide form. Okay, got it. Now as we move further, like we have potassium, sodium, calcium, magnesium, aluminium. Now we have titrated chromium and zinc, chromium and manganese. Then we have carbon here, and then zinc, iron, zinc, iron, tin, and lead. Okay, so we have zinc, iron, tin, lead. Okay, zinc is ZnO. But if you heat it, you have first roasted it. Okay, by using roasting, you have converted ZnS. When you heat it in the presence of oxygen, then you have converted it to ZnO plus SO2. Now, like previously, we cannot convert ZnO by simple heating. You cannot convert ZnO into Zn and O2 by simple heating, as we are doing in the case of and uh, silver and mercury. Okay, you cannot continuously heat it. If you continuously heat it, you will not get this one. Okay, you cannot get this one. Even if you use crushed ore, ZnS, like in case of copper, here this will not act as a reducing agent. Okay, we need some external reducing agent, which is powerful. Okay, got it?
Yes, sir.
So here in this case, we use carbon. We use carbon. Okay, carbon is suitable and it easily available and economical. So carbon is suitable reducing agent, which converted this ZnO into Zn, and CO2 gas will be released. Okay, like if we have lead PbO, then on applying carbon, you will get Pb plus CO2. And similarly, if we have Fe2O3 and then you heat it with carbon, you will get Fe plus CO2. So these are called mid-reactive metals, and carbon is written over it. So it means that these metals can be reduced with the help of carbon. Okay, so we can write it reduction with carbon, and these are called mid-reactive metals. Mid-reactive metals. And low reactive metals are just reduced by simple roasting, but mid-reactive metals can be reduced with the help of carbon. Okay, okay.
Yes, sir.
So note it down. Note it down.
Sir, what is after Fe?
After Fe is Sn. Sn is tin, and Pb is lead. Lead. So done.
1 minute, sir. Done, sir.
Done. Okay. So note it down. Smelting is called reduction with carbon. Mid-reactive metals oxide can't be reduced by simple heating. They require suitable reducing agent. Okay. And the reduction with carbon is called smelting. Please note this statement.
Sir, what is after suitable?
Suitable reagent for reduction. Note it fast.
Done, sir.
Done. Okay.
Yes,
So
sir.
let's move further. Then next one is, if we move further, that is after this these metals that are mid-reactive like zinc, zinc, iron, tin, and lead. We have written carbon here. So this carbon is written here. But above this, we have magnesium and chromium. And over this, we have aluminium. Okay. So what does it means? That chromium oxide cannot be reduced if we are having MnO2 and if you are having Cr2O3. So if you use carbon to it, carbon is below chromium, so it will not able to reduce. So here we use aluminium instead of carbon, but we use aluminium. You understood?
So,
So
like,
aluminium will be used for as a reducing agent in removing the oxygen from their manganese oxide and chromium oxide. Okay.
so
Okay.
like the mid ones will always go with carbon, and the least
Yeah.
one will go with oxygen, and the above one will go with aluminium, like
Yeah.
which
Yeah.
are
Yeah. 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 About between aluminium and carbon, we use this one. Okay. Very good.
okay, sir. Got it.
Now this is MnO2. Okay, MnO2, when you just take the powder of this one and powder of this aluminium, and they are mixed together. And when we initiate this reaction with burning of magnesium ribbon, we just put the burning magnesium ribbon in this container, and then this reaction starts. This reaction is so exothermic that the heat liberated out during this reaction let the metal get in liquid state. So this reaction is very means this a large amount of heat is being produced during this reaction. Okay, so this is called thermite reaction. You understood?
Yes, sir.
Okay, so this is called thermite reaction. So thermite reactions, we can consider that in thermite reactions, a large amount of heat is produced. Okay, and the metal obtained is in liquid state. Metal obtained is in liquid state. Like we have this chromium oxide, Cr2O3. So when you heat it with the burning ribbon, okay, and the mixture of this one, you will get Al2O3 and chromium in the liquid state. Okay, and this reduction with aluminum is called aluminothermy. Means like we reduction with carbon was called smelting. Like similarly, if we are reducing with aluminium, then it is called aluminothermy. And aluminothermy is very exothermic process. So reduction with aluminium is exothermic process. Heat liberated out during this reaction let the metal obtain in the molten form. Okay, and you need to keep in mind that iron comes in the mid reactive series. Okay, and
Yes, sir.
it can be reduced with the help of carbon.
Yes, sir.
But here the iron obtained is not in the liquid state. Okay, but
Yes.
if we heat this Fa2O3, okay, with aluminium, then the heat liberated out during this reaction is so large that the iron obtained is in liquid state, and this obtaining of iron in the liquid state help us for welding purpose. Okay, and this special reaction is called thermite reaction. We call it thermite reaction because here the iron obtained is in liquid state. We don't need a every time we don't have, for example, if you are just joining a railway track, so while joining a railway track, you need not to make every time a furnaces. Okay, railway track is in jungle. Okay, and it can be in jungle. So every time you cannot have a furnaces where you can melt the iron and then bring it. Okay, then it can again get condensed. Okay, and large amount of iron is being required. So we use thermite reaction. We have a container here which is filled with aluminium powder and Fe2O3 mixed together, and we heat. We just put it a burning magnesium ribbon over it, and then the heat liberated out during this reaction is so large that the iron obtained in this reaction is in melted form. Okay, and this reaction is called thermite reaction. Okay, so this so many times this reaction is being asked that what is thermite reaction. Thermite reaction is the reactions of aluminium and iron oxide Fe2O3 in which uh, the reaction take place and Al2 3 and iron is obtained in the liquid state, and this obtaining of iron in the liquid state states, okay, we called it this is used for joining the railway track, so please note it down in the copy.
Sir, its example is that it is used for joining railway tracks.
Yes, it is used for joining railway tracks and broken machineries,
Okay.
so please note it down. Note this whole process, then I'm going to show you thermite reaction. When you're done, please let me know. Okay, note in
Okay.
short notes. Okay, don't make it, try to make it short.
Done, sir.
Done. Okay, so
Yes.
here you can check that this is a thermite reaction that is taking place. Okay, and this tin is going to have that the person has put the burning magnesium ribbon, and this tin can is going to have a mixture of Al2O3, sorry, Al and Fe2O3, and this burning magnesium ribbon is put into this hole. The heat liberated out is so large that even this tin can melt. Okay, check it from the bottom. This is the thermite reaction that is taking place. that you can check that the metal, malted metal is coming here. Okay. And this is the molten form of iron that is coming. Okay, so this reaction is so exciting. Just burning a magnesium ribbon, you just put a magnesium ribbon, burning magnesium ribbon, and you can check that how much amount of heat is produced during this reaction. That it led the metals to obtain in the liquid state. Okay.
Yes, sir.
And this is called, which type of reaction is this? This is called thermite reaction. Okay.
Yes, sir.
Now moving to the next part here is the top reactive metals that are above aluminium. Like we have aluminium also. Like we were having aluminium, then we have chromium and manganese. We done it by aluminium. Now aluminium, the metal above aluminium like potassium, sodium, calcium, magnesium. So if they are in their oxide form, like Na is in Cl form, okay, Al2O3, like CaO. So they are very reactive metals, oxides, and they can't be reduced with the help of aluminium because aluminium comes below these. Okay, and we cannot use more reactive metal. For example, if you are having sodium, potassium oxide, calcium oxide, we want to get the calcium here, so we cannot reduce it with the help of sodium because sodium is more costlier than this one, than this calcium. So if we use instead of this one sodium, so if we use sodium, that will give you Na2O plus calcium. It will give you calcium, but here sodium will be lost. Okay, so we cannot use this method because sodium is expensive. We are spending more than obtaining the metal of that amount. So what we do here is in case of calcium, or if we are having sodium chloride, we take a molten. We called it electrolytic reduction. What we called it? Electrolytic lytic reduction method. Okay, so if we are having these top reactive metals, so we start we reduce it, we remove their oxygen or their halides. For example, if you're having Ca, this is magnesium oxide, this is Al2O3, and this is NaCl. So if we want to get the metal from these, what we do electrolytic reduction. What we do? Electrolytic
Electrolytic reduction method.
reduction. And what happened in this method? We just take the molten NaCl. For example, if I'm taking the example of NaCl because it is in the syllabus. So if we are having, there are two rods, one is positive rod, another one is negative. Okay. Okay, this is negative, this is positively charged, this is negatively charged. Negatively charged is called cathode. Cathode, and positively charged is called anode. Keep in mind that we have to use here molten NaCl. Molten, not, we are not going to use the aqueous NaCl, because if you use an aqueous NaCl, it will give you chlorine gas plus hydrogen gas plus caustic soda. That was the preparation of caustic soda. Okay, we use molten NaCl, and when we have molten NaCl, we will have Na positive and Cl minus, because in molten state NaCl ion will be dissociated into the ionic form. So we will have this Na positive and Cl minus ion. Okay, got it?
Yes, sir.
Got it? So at cathode, what is, sorry, at anode, what is going to happen? At anode, you will find that these
The
are the negatively charged ions.
ion
So these two Cl minus ion will goes at anode because it is negatively charged. Negatively charged will always move towards the positively charged rod, and it will lose two electrons from Cl2, and will lose two electrons. Okay, chlorine gas will be formed. And at cathode, what would happen?
the Na would go and attach.
Two Na positive will get these two electrons, because each Na ion, when get one electron, it will go forms Na solid. Okay, so Na ion will get converted into Na solid by getting one electron. So there are the two Na ions, and they will get two electron from this one, and will form two Na solids. Okay, so overall reaction, we can write overall reaction. Overall reaction here is 2 NaCl when, and in the liquid state, 2 NaCl in the liquid state. When you heat it, electricity is passed, then you get 2 Na solid plus Cl2 plus Cl2. Yes, note it down.
So should I draw the diagram?
Yeah, you have to draw this diagram also.
Okay, sir.
Cl will move here and Na will move towards cathode. Done?
Yes, sir.
Okay. So in the electrolytic reduction, what we does, you have to note it down. Note this one. In this method, molten ore is taken in the electrolytic cell. We are just writing electrolytic reduction. Okay, note it down. Last statement. In this method, molten metals ore is taken in the electrolytic cells. When electricity is passed, the metals ions get reduced to metals solid at cathode. Done?
So 1 second, sir. Done, sir.
Okay. Now by using various methods like simple roasting, okay, like simple roasting, okay, we have done various method uh, to uh, obtain metals from their oxide forms, okay, like by simple roasting, by smelting when we reduction with carbon, for the mid reactive metals, For manganese and chromium, we use aluminium. And for the highly reactive metals, we use electrolytic reductions. Okay. Now here the metal obtained that we are obtaining is not in the 100%. We are not saying that it is 100% pure. Okay. So 100% pure means does not mean that it is going to have impurities like sand. No. Impurities here it means that it is not going to have atoms of the same elements. For example, if I'm having this copper strip, so it is if it is having copper as well as some atoms of silver, gold, okay, so it is not pure. It is not pure because it is having some atoms of gold and platinum also. Okay, so this will be considered as impure. Okay, so
Yes.
we use the last method for this one is electrolytic refining. Electrolytic refining. And what we does in electrolytic refining, let me show you. That in electro means you have to use electricity, and refining means we have to refine the metal. So what we does here is we take a metal that we are just purifying. For example, if we are just purifying the copper, okay, okay, so we take two rods, and one is the impure rods. We are just making like this impure rod, okay, and very thin a very thin pure metal rod of the same metal that we are refining. Okay, so we take this one as pure and we made it positively charged. We connected with positive, and this is anode, and
It
this is
cannot be negatively charged.
which one?
The
Cathode is
an the impure metal cannot be negatively
no, no,
charged.
no, 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 no. We have to keep it always positive charge. Impure metal rod. This is must, and this is so many times this question is being asked. Okay, so we cannot interchange it. Now this is a rod, thin metal rod, which is of same metal that we are purifying. Okay, got it?
Yes, sir.
And now we are just connecting this with the negatively charged. And you have to keep in mind here that on the right hand side, we used to write, and you have to write it that on the right hand side, we always keep the anode. Okay. And in the left hand side, we always keep the cathode. Okay. Don't interchange
Yes,
this
sir.
one also. And this is cathode, and it is of same metal, pure. This is pure metal rod, which we are refining. For example, if we are refining copper, so we'll take this rod as copper. If we are refining silver, then we will take this rod of silver. Similarly, if we are refining copper here, so this will be the copper rod, impure rod, which we are refining. For example, it is having copper atoms, some gold, some silver atoms. Okay. Okay. Then platinum, then copper. So it is going to have more copper atoms, but some amount of silver and platinum atoms. Okay. And this is going to have pure copper atoms. Now, coming to the point that we also use the same metal salt electrolyte. In the electrolyte, the solution that we are using here, this will be of same metals salt. For example, if we are using copper, then we will use copper sulfate. If we are refining copper metals, okay. If we have refining this one silver, then this will be of silver nitrate AgNO3. So depending on the type that the metal that we are purifying here, the same metal salt is required. Okay,
Sir,
got
why
it?
can't we use NaCl or the salt solution?
Any other salt solution that's I'm going to explain you that why. Let me explain you this one also. For example, this one is copper atoms, Cu2 positive atoms. For example, if it is going to have salt solution, that is copper sulfate we have taken. So Cu2 positive, it will be going to have SO4 minus 2, because when we are having this copper sulfate, CuSO4 in this one, then it will get dissociated into Cu2 positive and SO4 minus 2 ion. Okay.
Yes, sir.
Okay. So Cu2 positive, SO4 minus 2. So this is going to have this type of atoms. Okay. Now what is going to happen here is that on passing electric current, what would happen? This blue color copper ion. So let me write cathode. At cathode, on passing electricity, cathode is negatively charged, and this one is negatively charged. This blue color copper ions, okay, this blue color copper ion, this is positively charged, will start moving toward the cathode. Hmm?
Yes, sir.
So what do you think that at cathode is going to happen?
It will gain the copper.
It will gain the 2 electron from and will convert it into copper solid,
Yes, sir.
which is brown in color, which is brown in color. So it will get converted into copper solid, and it will start depositing on the surface of this one. Okay, on the surface of this one. So slowly the copper ions of the solution are getting converted into copper solid. Okay, now you understood that
Yes.
if we take the silver, then the layer of silver will be deposited.
Yes,
So
sir.
okay, so we have to take the copper solution so that the copper ions are depositing over the copper. Okay,
Yes, sir.
and why we are taking the pure metal rod as cathode? Why we are not taking this one as impure?
If impure is there, it will not form a layer or a coating, sir.
Yeah, it will form a layer of pure, but inside it is again impure. So how can we say that it's pure? If we are having something inside this atoms are depositing over this rod. If it is of iron, then it will be again depositing on the iron. So how can we say that it is of pure copper if we are not having inside rod of pure? So we should have this inside rod of pure metal, so that the layer that is we are depositing will be depositing on the pure, and the whole rod will become pure. Okay.
Yes, sir.
Okay. Now you see that if the copper ions are start moving from this one, moving here. Okay. You see that if they start moving here, then the concentration of Cu2 positive ion will decreases in the solution.
Yes, sir.
And if it start decreasing, the concentration of Cu2 positives is decreasing, then what would going to happen? Tell me, what would be going to happen?
The sulfate would increase.
Sulfate ion concentration will increase. And do you think
Yes,
that sulfate ion is very stable ion? Sulfate ion is very stable ion. It does not reduce its charge. Okay, like in the previous, the Cl minus was going on the anode. Okay, and this was using forming chlorine gas in the electrolytic reduction
yes,
of
sir.
NaCl. But here the sulfate ion will not go. Then what would happen in order to maintain the electrical neutrality? The copper atoms that are here, okay, why not the gold and platinum atom will lose
Because
electron?
the impure, sir, and copper sulfate solution is there in the.
No, because if we ask to lose the electrons, we have this reactivity series: copper, silver, gold, platinum. Okay, so if we ask that this is more reactive than this one, silver, copper is more reactive than silver. How can we
Yes,
say that? This reactivity series is only based on the basis that the element that will lose first electron will be considered as more reactive. So copper is more reactive than silver because it can easily lose electron, more easily electron than silver. Okay. So unless and until we are having copper atoms here, the copper atom will lose electron first. Okay. Got it?
yes,
So
sir.
we can say that at anode, what would happen? The copper solid, which is copper solid brown in color, will loses its electron and will form copper 2 positive ion, and the 2 electrons will be replaced. So this copper atom will be converting into copper ion. This copper atom will be converting into copper ion. So from the solution, it is going into the on the rod, on the cathode. Okay, and the equal amount of copper atoms are converted into copper ions. So you can say that the copper ions from the copper solid solutions are getting converted into copper solid, and it is depositing on the cathode, and the equal amount of, in order to maintain the electrical neutrality of the solution, the equal amount of copper atoms from the rod, from this impure rod, are losing their electron. They are converting into their copper ions, and this process remain continue. From this one it is going to here, and from this one at last we will find that this rod will become more thicker. At last we'll find that that the this rod will become more thicker, the cathode will become more thicker, and the impure rod will disintegrate. This will disintegrate. Okay.
So
You
what will
understood?
happen to the impurities if they are refined?
Yeah. The impurities like gold, platinums here, they will settle down. They will settle down here. Okay, like gold, platinum, they will settle down here and they will form inert mud. So the impurities will settle down and called inert mud. Inert mud. Okay, inert mud.
Yes, sir.
Called it inert mud. So they will settle below the inert mud and they one by one. So this is what we does in the electrolytic refining of copper. So please, you can make this diagram or please make the previous diagram. Yeah, that I have made here. Please make this diagram first. Done?
No, sir, 1 minute. Done, sir.
Done. Okay. Then please note it down. Write a note on electrolytic refining of copper. Fast.
Sir, can I take a screenshot of it?
Yes, you can take a screenshot. Take the screenshot.
Yes.
Done. And you have to note it down later. But note it down,
Yes.
please. Okay. Have you taken this
Mm.
one? Take this
No,
one
sir.
also. Take this one also. Done.
Yes, sir.
This one also. Have you taken this one? This one?
No, sir, I wrote it.
Take it. Write a note on electrolytic refining of copper.
Yes, I took this one.
Okay, okay. So now moving to the next part is of this one is alloys. What are alloys?
Mixture,
Alloys. We can say that alloys.
homogeneous mixture.
Yes, these are the homogeneous mixtures of two or more metals or metals and non-metals. Okay. Alloys are homogeneous mixtures of two or more metals or metals and non-metals. Metals and non-metals. Okay. You understood?
Yes, sir.
So for example of two metals only, like we have brass. Brass is a homogeneous mixtures. It is made when copper and zinc are mixed. Bronze, when copper and tin are mixed. We have another examples like stainless steel. No, steel is an example of when metals and non-metals are mixed. Steel. Only steel, not about stainless steel. When we have carbon and iron. We can say that iron plus carbon are mixed together, they form steel. Okay. So steel is an alloy. Like similarly, we have solder when
Sir,
tin and
aluminium is an amphoteric oxide, right?
yes, aluminium oxide is an amphoteric oxide.
So they don't belong to alloys, right?
No, they don't belong to alloys.
Okay, sir.
Amphoteric oxide is the oxide that shows both acidic as well as basic behavior. Okay.
Yes, sir, got it.
Now these are the homogeneous mixtures of two or more metals or metals. Okay. And let me tell you that when one of the constituent of alloy is uh, we can say that amalgam. What is amalgam? Amalgam. So amalgam is an alloy. We can say that it is an alloy in which one of the constituent is mercury. Okay. Alloy in which one of the constituent is mercury. You understood? Mercury. So if we have sodium
Mm.
amalgam, we have sodium plus mercury. Example, sodium amalgam. Sodium amalgam. And ferrous alloys are those alloys in which one of the constituent is ferrous alloys. One of the constituent, put it down, constituent is iron. Okay, like steel. Example, steel. Okay, got it?
Yes,
So
sir.
why we are making alloys? Why we are making alloys? In order to increase the tensile strength, durability, in order to get the metals. For example, we need to make this spacecraft. Okay, aircraft. We need to make the aircraft, and for making aircraft, we need some alloys. Okay, that should be very durable and strong, but it should be of very light in weight. Then we make magnesium, 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 which is an alloy, and it is used for making aircraft. Okay, alloy, and it is made from magnesium plus aluminium. When mixed together, they form alloy. Okay, magnesium. Similarly, solder. Solder is an alloy of tin and lead. Tin, this is tin and lead, and it is used. It has low melting point, and good conductor. Good conductor. So it is used for soldering, used for soldering wires in electric appliances, in electrical appliances, okay?
Yes, sir.
In electrical appliances. So we have different types of alloys. Okay, I'm going to show you here that please take the screenshot of that one, and you have to,
Sir, can you move to the previous parasalloy?
yeah, moving. Wait a minute.
Sir,
Yeah, noted. Noted.
done, sir.
Done.
Yes,
This
sir.
one. Have you taken the screenshot?
Sir, 1 second. Done, sir.
And here I'm just going to give you here one more. Please take the screenshot of this one also. And these are the ores, and you have to only wait a minute. Don't take the screenshot. Let me mark first. Okay. This is the bauxite you have to memorize. Zinc blend, copper pyrite, and then magnesite can be asked that it is an ore for formula, and the ore name should be used. Horn silver, pyrolusite, pyrolusite will not be asked. And then hematite, then rock salt, cinnabar, galena, limestone, and limestone only. Okay. Gypsum is for calcium. So these ores are very important. So please write their names in the copy, and you should remember the name. That horn silver is used for is an ore for silver. Okay.